In this video, we'll work out two examples of finding general solutions, solving initial value problems, and sketching phase portraits for constant coefficient systems. The first one we're going to solve is this one here. If x prime is 0, 2, minus 2, 4 times x. So our first step is always to find the eigenvalues, which are given by 0 minus lambda minus 4 minus lambda plus 4 equals 0. This is lambda squared plus 4 lambda plus 4 equals 0, which is a double root at minus 2, which means we are going to get an improper nodal sink here because we have a repeated eigenvalue and it is negative. Now let's look for an eigenvector. So for this, we are adding 2 on the diagonal. So we'll get 2, 2, minus 2, minus 2, which reduces to 1, 1, 0, 0. So an eigenvector here is 1 minus 1. Now, since we only found the one eigenvector, we're going to also need a generalized eigenvector, so let's just find that now. And that will come down to the same matrix, 2, 2, minus 2, minus 2, equaling 1 minus 1. This reduces to 2, 2, 1, 0, 0, 0, or that 2w1 plus 2w2 equals 1. For this, we can choose w1 equaling 1/2 and w2 equals 0. That solves this equation, so we're fine. And so our vector here is going to be 1/2 and 0. Putting all this together means I can write the general solution. X of t is going to be c1 times our eigenvector 1 minus 1 e to the minus 2t plus c2 eigenvector t e to the minus 2t plus our generalized eigenvector 1/2 and 0 e to the minus 2t. And with that, I can now sketch the phase portrait. Draw on our axes. We have our straight line at 1 minus 1, so that's off this way, and it's coming in. And we can rewrite our non-straight line solution as t plus 1/2 and negative t times e to the minus 2t. So at t equals 0, that is at 1/2 comma 0. That's going to be over here somewhere. And as t gets bigger, the first component will always be positive, and the second will always be negative for t bigger than 0. This means that for t positive, this is going to be in quadrant 4. And as t is positive, my solution is going in towards 0 because I have an e to the minus 2t term on the front. This means I'm going to come in towards 0 in quadrant 4 and along the line like that. If t is less than 0, I will see that this is in quadrant 1 at first, while t is less than 1/2. And then when t gets to be less than minus 1/2, this is negative, this is positive, putting me in quadrant 2. So I'm going to go quadrant 2 out this way, coming in like that. With one of these drawn in, I can then draw the symmetric version on the other side and fill in some more curves for this figure. And there is our improper nodal sink for this equation. That gives us one example that involves repeated roots. For a second example, we're going to solve an initial value problem, but we will still sketch a phase portrait anyway to round out the problem. We have the problem here, x prime is 1 minus 425 times x, the integration at 3, 2. So our first step, as always, is to look for the eigenvalues, which in this case are given by 1 minus lambda, 5 minus lambda, plus 8 equals 0, lambda squared minus 6 lambda plus 5 plus 8, or lambda squared minus 6 lambda plus 13 equals 0. That doesn't factor. So the quadratic formula tells us that lambda should equal 6 plus or minus square root of 36 minus 4 times 13 is 52. All over 2. This is 6 plus or minus square root of minus 16 over 2, or 3 plus or minus 2i. So we are in the complex case, which means you'll have to find one eigenvector, and we'll get the other one as for free, and we'll have to convert this into a real valid solution once we get there. Right now that we can see, this will be a spiral source because the real part of the eigenvalue is positive. Let's look for that eigenvector. I'm going to take the plus eigenvalue, and subtracting that off the diagonal gives me 1 minus 3 plus 2i minus 4, 2, 5 minus 3 plus 2i. I can then combine the complex numbers together. I'm going to divide the first row by minus 2 and the second row by 2, which gives me 1 plus I, 2, 1, and 1 minus I. And if I multiply the first row by a 1 minus I, the conjugate of 1 plus I, this will become 1 plus I minus I plus 1 is 2. 2 times 1 minus I, 1, 1 minus I, and we see these rows are in fact redundant. Therefore, I can take the second equation here, which will tell me that v1 plus 1 minus I v2 equals 0. And so one example of something I can take for an eigenvector here is I can take v1 to be 1 minus I and v2 to be minus 1. That'll cancel those out and give me 0. So I will take my vector to be exactly that, 1 minus I and minus 1. Now this means that I have a complex solution of the form x of t equals 1 minus I and minus 1 e to the 3 plus 2i t. Now I have to break this up into real and imaginary parts to get my two real solutions that I can use to write my general solution. So we apply Euler's formula, splitting the e to the 2it into cosine 2t plus I sine of 2t. Then we are going to distribute this into both the top and bottom part of the vector and FOIL this top row out. Then I can divide this into real and imaginary parts to get my two separate solutions. For the real parts, I take this cosine, this sine, and the cosine down here. And for the imaginary parts, I take the remaining terms, this sine, this cosine, and this sine. Then I can call this guy my first solution x1, this is my second solution x2, and I can then write my general solution. So now we need to solve the initial value problem. In the initial value problem tells us we also wanted x of 0 to be the vector 3, 2. And we solved this in the same way we solved initial value problems before. Let's plug in 0 and then find c1 and c2 to make this work. So if I plug in 0 to my solution up here, I get c1 times cosines go to 1, sines go to 0, and exponentials also go to 1. So I'll get c1 times 1 minus 1, because cosine and cosine, plus c2 minus 1 and 0. Then writing this out as a system of equations tells me that I need 3 equaling c1 minus c2, and 2 equaling negative c1. So c1 is minus 2, and c2 is minus 5. That's what I get out of solving that system there, because c1 is minus 2, plug that in, add it over, get 5 equals negative c2. c2 is minus 5. So that means the solution to the initial value problem is negative 2 times our first solution, and then minus 5 times our second solution. It can be left like this, or you can combine some terms because you'll see that there are terms that match this cosine and this cosine, this sine, this sine. So you want to write a single vector, you can collapse some terms together and get a solution in the form like this. On the top, I see a negative 2 cosine and minus 5 negative cosine, so that ends up being a plus 3. For sines, I see minus 2 and minus 5, so minus 7. On the bottom, there's as they are, 2 e to the 3t cosine of 2t plus 5 e to the 3t sine of 2t. And so either of those would work as a solution to the initial value problem. Now, as a last point, let's sketch the phase portrait here. So here's our general solution. It's going to be a spiral source, we know that. So let's look at this guy here to see if we're spiraling clockwise or counterclockwise. So let's draw on some axes. At t equals 0, the solution here is at 1 comma minus 1, which is 1 in the x minus 1 in the y is down here. Then if we look at t equals pi over 4, when the cosine terms will go to 0, I end up with 1 times e to the 3 pi over 4 in the first component and 0 in the second. So the y has gone to 0 and the x has stayed positive. So on the axis, we are then up here, and it's away from 0 because we're spiraling outward as t gets bigger. And that there gives us a direction. We could check more points, but we keep following the same pattern. the spiral out goes this way, and the spiral in must wrap around in this direction here. You could take the other one too. It starts at -1, 0, so it starts over here. You would see the exact same pattern. The spiral goes out in that direction and goes in around this way. So there's our spiral source for this problem and how we sketch the phase portrait from it, as well as how we solve the initial value problem that corresponds to it by solving for the C1 and C2 as we need to meet the initial conditions.